Welcome to a screencast on nuclear energy. Now, we've talked a little bit, or just mentioned nuclear fission. Large nuclei can undergo what's called nuclear fission, which is fragmenting into smaller pieces. Here is a sample example of nuclear fission, where a plutonium nucleus is hit with a neutron, and it breaks apart into a cerium nucleus, a krypton nucleus, and two neutrons. And you should double check that the mass numbers add up to the same on both sides of this equation as do the atomic numbers. And these are Lisa Meitner and Otto Hahn, who were two of the scientists who first discovered nuclear fission. Here's an image of what happens. Big plutonium nucleus hit with a neutron, breaks apart into smaller chunks, and a couple more neutrons, 2 or 3 typically, come out as a part of this fission reaction. And a mass energy calculation for this process. There's the mass of a neutron, mass of krypton, mass of cerium. We have to pick the right isotope. And then mass of plutonium. These are values we can look up on tables or might be given to you in a problem if you're supposed to solve it. And then this is pretty much what we've done before, and it's actually even a little more straightforward. Energy change for this nuclear reaction. The plutonium 239 plus the neutron have a total mass that we can add up these two particles. And then the cerium, the krypton, and the neutron, we can also add up their total masses, and what we get is 240.0093 grams. This is per 1 mole of plutonium and 1 mole of neutrons, makes 239.7843 grams for 1 mole of cerium, 1 mole of krypton, and 2 moles of neutrons. Notice that grams per mole values are the same as AMU per nucleon or per particle. So this gives us 0.2249 grams of mass lost, negative sign because the mass has gone down. And then to calculate the energy that is released by this process, we use the Einstein equation. And note, we have to do the mass change in kilograms if we would like to get joules, which is typical, because kilogram meter squared per second squared gives us joules. And these are big enough numbers that we sometimes turn them into kilojoules instead. So negative 2.021 times 10 to the 10th kilojoules of energy, so about 20 billion kilojoules of energy are given off when 1 mole of plutonium 239 undergoes this nuclear fission reaction. Massive, massive amounts of energy. Okay. There's another picture of the nuclear fission process. And then notice, since the nucleus takes in a neutron, splits into smaller pieces, and emits several more neutrons, what can happen is we can get what's called a nuclear chain reaction. So one neutron splits one nucleus, which provides 2 or 3 more neutrons, which split 2 or 3 more nuclei, each of which then can split 2 or 3 more nuclei, and we get this sort of cascading chain reaction. And this nuclear chain reaction can power a nuclear power plant if we control it. Lots and lots of energy from the conversion of mass into energy in a nuclear fission reaction. If we control it, that's a power plant. If we don't control it, we get a nuclear bomb. And the difference between a bomb and a power plant has to do with how they're put together. And the key thing is, in a nuclear bomb, we get what's called a critical mass. And in a nuclear power plant, we ensure that a critical mass cannot happen. And what a critical mass is, we can see the distinction if we have too small a mass, which is below critical. So here is our mass of stuff, and with our mass of stuff, if a neutron hits a nucleus, it breaks apart and emits more neutrons. Those neutrons can break apart other nuclei. If the amount of material we have is too small, too many of the neutrons escape from the material. They're not then able to break apart other nuclei, and this is what's called a subcritical mass, and the chain reaction stops if the mass is that small. Now, if we get a big enough mass, this is what we call a critical mass, or beyond that, a supercritical mass. What happens is a neutron comes in, breaks apart a nucleus. That produces neutrons that can break apart further nuclei, and if the mass, the amount of material is big enough, then not that many neutrons escape, and we get this out-of-control chain reaction. So to make a nuclear bomb, you essentially have a source of neutrons, and then you find a way to assemble enough nuclear material very quickly to make a supercritical mass, which will then explode. Okay, now on the other end of the spectrum, we have some small nuclei that can undergo nuclear fusion. That's a combination of small nuclei. Here is an example of a fusion reaction. The isotope hydrogen-2 combines with another hydrogen-2 to make the slightly larger helium isotope, He3, and a neutron. And there's all kinds of possible fusion reactions. They're always going to be small nuclei making bigger nuclei. The key thing to note is to make a fusion reaction happen, you need very, very high temperatures to force the nuclei together, and fusion reactions need this high energy, and that can be found in stars and in particular our sun. And so fusion reactions actually provide the energy from our sun. So far on Earth, we haven't figured out how to contain the small nuclei to achieve high enough temperatures without using lots and lots of energy to do that. So we've achieved fusion reactions on a small scale, but so far haven't gotten more energy back out of them than it has cost us to make the fusion reaction occur. And their fusion occurs using strong electric and magnetic fields in what's called a tokamak, which is, here's an example of one at Princeton, and it's buried inside all of this fancy electronics. Small amount of fusion can happen in there. And that's it for the screencast on nuclear energy.